I'd like to introduce the IoT platform Plato that uses mruby. My name is Hiroshi Mimaki, and I belong to SCSK Kyushu Corporation and the specified non-profit organization mruby Forum. First of all, I'd like to talk about the IoT. This figure shows the service structure of IoT. In order to realize IoT services, it is necessary to integrate the cloud, network, and devices. Creating all of this is extremely difficult and needs both technically and laboriously. Many services are provided on the cloud side, and it is possible to utilize them via REST API and MQTT. It's becoming standard. However, in the area from devices to networks, there are few effective platforms that can be called standard. Therefore, we have developed the IoT platform Plato. Plato was jointly developed by Braebridge, Kyushu Institute of Technology, International Laboratory Corporation, and my company SCSK Kyushu, with the support of the Ministry of Economy, Trade and Industry Support Project. Plato features support Bluetooth 5.0, that is long-range version, and LoRaWAN network. By drag and drop, Plato generates IoT applications with a very easy GUI. Support security function. Next, I will explain the constitution of Plato's IoT network. Edge devices with sensors connect to the bridge device via Bluetooth. Bluetooth can communicate in long-range mode and can communicate up to about 1 kilometer. The Bluetooth LoRa bridge relays the sensing data received via Bluetooth via LoRa. Then it reaches the internet from the LoRa gateway. Since the transmission distance of LoRa is about several kilometers, it is possible to build a wide area IoT network by using Plato's edge devices and bridges. Even if you cannot use LoRa communication service, you can build a network using private LoRa by purchasing a commercially available LoRa gateway. This is the hardware specification of Plato device. The edge device and bridge are almost the same in terms of hardware. The SoC is Nordic's NRF52840 and controller is ARM Cortex-M4. It has 1 MB ROM and 256 KB RAM. With 256 KB of RAM, mruby 3.0 will work, but mruby 2.1 at the time of this development was difficult to run the application. Therefore, in Plato development, we adopted mruby/C, which can operate with low memory. mruby/C is a smaller mruby, and Mr. Tanaka will explain this after this session. The device interface supports GPIO, UART, I2C, and SPI, and various sensors and GPS are connected to it. And this is Plato's software structure. We installed a mruby/C virtual machine in the firmware and ran the Plato framework on it. The version of mruby/C is 2.1. The Plato framework includes an application framework and a device class library. The above is the software provided by Plato. IoT applications can be freely created by the user and written to the device using the Plato GUI. The following is a brief description of the basic structure of the Plato application. Plato has defined three elements which are sensor, timing, and action. Those make up an IoT application. Each of these three elements defines what, when, and what to do. We have made it possible to building an application by grouping these three elements into a unit called job, and operating multiple jobs in parallel or in conjunction with each other. Let's take a look at the demonstration from creating to executing an IoT application using Plato. Now, create an application using Plato. First, select Create Application. The basic information setting screen of an application is displayed. This time, I'll create an application that periodically acquires temperatures and humidity. So the application name is TempHumi. Group settings are network settings. Although detailed explanation are omitted. This time, select the pre-registered group 1 and click Next. Next is job registration. Register job by selecting in the order of sensor, timing, and action introduced earlier. Add temperature and humidity from sensor. From timing, specify interval and set the time to 5 seconds so that the operation is easy to understand. From action, specify Bluetooth transmission and register job. The jobs added to the job list screen are displayed. It is possible to add multiple jobs, but this time I will create an application only with this job. Check the contents of the application confirmation screen and click Create to generate the application and display the source code in Visual Studio Code. Create a job sensing temperature and humidity every 5 seconds. Sent via Bluetooth. You can see that the code was generated. The generated Ruby application is compiled into binary. Now, let's write the generated application to the Plato device and see how it works. This is Plato's edge device. Click Deploy Application to launch the transfer tool. First, select the device in Scan Plato device. Then, under Select Application Binary, select the TempHumi application binary. TempHumi. Click Deploy to start transfer to application. During the transfer, the LED of the device flashes blue, and when transfer is completely succeed, it finally it flashes yellow. Now that the application has been written, let's check the operation using the simple viewer. Select the device as before and start data notification. You can see that temperature and humidity are displayed every 5 seconds. You can see that value changes when I touch the sensor part. In this way, Plato allows you to create IoT applications and write to device with simple operation. Next, I'd like to introduce how to realize device access with mruby/c. First, the application calls the sensor class. The sensor of the edge device is connected by I2C and acquires data via I2C class. The I2C class is implemented in Ruby and C, and it is possible to control the I2C device by calling the I2C communication process implemented in firmware from the process implemented by C language. Sensor classes that use I2C will be able to controlled only by classes implemented in Ruby. Similarly, for UART and SPI, by preparing a class for device interface, the device class can be implemented only with Ruby. Now, I'll briefly introduce the device class implementation of the temperature and humidity sensor. This is the device class of the temperature and humidity sensor, SHTC1. The read temperature method, I2C read command calculates the temperature based on the temperature data read from the SHTC1 sensor via I2C. Next, let's take a look at the I2C class. This is part of the Ruby implementation of the I2C class. The read command method calls two C implementation methods, _write and _read, to write the command and read the result. And this is the C implementation of the I2C class. This is a process at initialization, which defines the I2C class and I2C _write _read. When the _write and _read methods are called, the C functions C I2C row write and C I2C row read are called. And this C I2C row read is the C function called by I2C _read. In this process, device control from Ruby code is realized by calling the I2C read process of firmware. Once the I2C class is created in this way, device is controlled to I2C can be operated only with Ruby. If provided device interface classes for SPI and UART, you can easily implement the device classes themselves. I think it is one of the big advantages of using mruby/c and mruby in embedded development. And the end of description, it is a summary. With Plato, you can create IoT apps with a simple GUI operation. You can control the device with mruby. The strength of mruby is that it can be used by incorporating it into a C programs. You can extend your application simply by running a virtual machine on the firmware. Developers are also happy to be able to create a hybrid configuration in which controls are written in C and applications are written in Ruby. And the future of Plato. Small IoT using only Bluetooth. LTE-M and mruby3 support. This is the introduction of the IoT platform Plato that uses mruby. Thank you.